Hi class, this is 20.5 and we're going to look at cell potential, free energy, and the equilibrium constant. So when we look at, excuse me, this page here, there are some important relationships that occur between cell potential, free energy, and the equilibrium constant. So if you don't remember delta G, excuse me, I still have this cold. It just lingers. For the most part, I'm okay, but it comes up. Excuse me. So if you remember chapter 19, this delta G for reaction, it equals the maximum useful work of a reaction. And but what we're doing, the work here is electrical work, and that's where this portion comes in, where N is the number of moles of electrons that are transferred in reaction. We have Faraday's constant, which we'll cover later. And then we have the standard potential. So E with the cell. Now, I'm sorry. Sorry, this is the cell potential. Now, and when we have them under standard conditions, then you see that nice little dot in the superscript, and that means that they have to be under those certain conditions, which we should already be familiar with. Faraday's constant is here. It's coulombs over moles of electrons. And that's nice because it's a constant. So here is a little diagram to show you how these are related. And if you wanted to go from one to the other, you could use these equations to do that. So if you needed to discover the equilibrium constant, you would be given enough information that you could isolate K and plug that in. For instance, if you wanted to know, excuse me, any of the others, the cell potential or the free energy, you would be able to determine these just plugging this in. And that's what we're going to do here. These are some examples. So when you want a spontaneous reaction, remember that we want delta G to be less than 0. We want, it's got to be negative. It's easily said. If we want a cell potential, it's got to be positive, and we want the equilibrium constant to be above 1. So these are the conditions that we are interested in order to have a spontaneous oxidation reduction reaction. When we look here, again, this is just breaking down this information so you can see here what these stand for. Okay, so obviously if it doesn't meet these conditions, then that means that you're looking at something that is non-spontaneous. So if it's non-spontaneous, this is going to be positive, this is going to be negative, and this is going to be less than 1. So everything that's the exact opposite is going to mean that it's non-spontaneous. Okay, so again, this is just breaking down the same information and showing you the RF. So we substitute the values for R, which I'll show you in one of the problems, and the Faraday's constant and the temperature if we need to do that. If you actually plug in these values, you can have a standard formula for this. And you can use this by plugging in whatever else you need to in order to determine whatever it is that's asking. So this is a shortcut that you could have if you understand how all of these were plugged into it. Okay. So I'm going to show you some examples. Some of the examples are taken from another book, but they show examples that your book doesn't give me. So when it refers to 19.8, it's 19.8 in another book. Okay, so here's the sample. We have actually covered this in the previous section, and this was to determine the cell potential. It's positive, so this is, excuse me, this is spontaneous in the forward reaction. So this is good. This is a positive number here. And that's what we want in the overall of the cell potential. So we're going to take this information. So this is just a review, because if you see the question, it refers back to the information from example 19.8. And that's actually what this is. I just remove a lot of this stuff to make it work for us. But if you have to refer back to it, here it is. So what it's asking for is to calculate the standard free energy change. So we're going to take one of the formulas that we have on here, right here, and we're going to plug it in. Now, so we're going to take here. So we have the value. So we're trying to calculate the standard free energy. Now, we have 2 moles. So if we base it on here, you can see we have 2 electrons. So that's where the 2 moles come in. We have Faraday's constant right here. We have the negative value. And we have the cell potential from the previous problem that I just showed you. So now we're going to plug all this in. Remember, 1 joule is equal to 1 coulomb per volt. And we're going to plug that in. And this ends up giving us a negative 212 kilojoules. So let's go back and see what the free energy is on the conditions. We want it to be negative. So that's a good thing. For a spontaneous reaction, we want the free energy to be negative. And we want this one to be positive. That one's positive. This one's negative. So far it's working. Now the equilibrium constant, what if we wanted to solve for the equilibrium constant? So these are not really difficult problems. You just have to figure out which one it's asking and plug that information in. It's really not this, you guys have done far more difficult stuff. So we're going to use this problem, and this is just showing you how we replace some of the information here, which I'm just going to show you the formulas. So again, now we're going to calculate the equilibrium constant using the same information from example 19.8. So here we have it. Now, this is different than the way to do it in your book. So I have actually pulled the problem from your book as well. It's not the formula is a little different, but how you do it is not. So here is in our book is 20.5, but this one here is not matching what's in our book. So I'm going to show you with this one. Again, but in the end, it should be the same. So this is just showing you how we get this information. This is the problem that is being asked for to use in this one. So I put a box around it so you can see. Now we're just going to plug everything in. So we have 2, we have Faraday's constant, we have the cell potential, we have R, which is the gas constant, we have the temperature. We plug all that in, plug that into the exponent, and it gives us our value. So this is a formula used in another book. But it does show up into this point. I show you this one here, and I think it even shows you up to this point, but it doesn't show the book in this one. Now, this is from our book, and it uses the shortcut. Remember, it plugs everything in. And now we move everything around and use this one. So that's why I want to show you. This is straight from our book. It's example 20.7. I don't remember what page this is on, but we're going to plug in all this information. So it's just showing you the stepping stones to determine what we need to solve for this. So here is the actual reaction, the oxidation and the reduction. We have 2 electrons. We have the cell potential for the half reactions. And then we have the final one, which gives us our cell potential for the total. We're going to use this one, which is in the box. And now we're just going to plug everything in that we can. So here is the cell potential. Here is, we're solving for K, so that's why everything's flipped here. And we have the volts that were given to us. Plug it in. So this might be a little easier than the other one. It just depends on what you're comfortable with. Now we have this. We can solve for this, the inverse log, and it gives us our value. And this is what is given to explain what this would be. So there's 2 different ways. The formulas are a little different, but the answers and everything and the steps are mostly the same. So it just depends on which one you're comfortable with. So that's why I'm showing both. Determine the standard potential of a redox involving a transfer of 1 mole electrons with an equilibrium constant of 230. So this one's really not in your book, but it's still related to it. So it's giving us an idea of what we expect as the answer. This is a very small equilibrium constant. It is large, but it's not as large as some of the other ones that have a lot of trail of zeros. And we expect, so K is small. It's rather on the small side, even if it is spontaneous for that condition. But we also expect the cell potential to be above 1, which it means that it's spontaneous. But we also expect that to be small based on the equilibrium constant. So even though it's shifting to the right, it is not shifting a lot. So here we go. We can plug in everything in, which is the constants that we have for the standard conditions. And that will give us a value of 0.143. So it is positive. However, it's a very low positive value. So again, here is just a review to show you all the formulas. It's not too bad. Once you have all of the information, if it's under standard conditions, they don't really change. We've been covering standard conditions, and you've covered them in STP conditions for gases and stuff. So you should already be familiar with that. Okay, so cell potentials are related to changes in free energy, and it gives us the formula. And if it's in the standard state, we use standard state conditions. N is the number of moles of electrons transferred in a balanced equation. F is Faraday's constant, and it is in units of charge per mole of electrons. Spontaneous processes are associated with positive values of E and negative values of free energy. The cell potentials are related to equilibrium constants, and it shows you the formulas of how these are related with these relations.